Okay, so I see it's 29 minutes after the hour, so we can keep track of timestamps now when we go back and look at this stuff. In fact, here, let me just put in. Well, I put in 39. I meant to put in 30. Here, let me do that again. 30. Okay, so it says, it's at 8 on mine. It says 8:30, and it says :30. Okay, so we were talking about CAN buses. I'll tell you what I know about CAN buses. You can, if you're going to run an Arduino does not have a CAN bus peripheral built into it. So you have to go out and buy one of those little $5 boards that has a microchip, CAN controller, and a CAN transceiver on the thing. And you hook like 4 or 5 wires between the two. And by downloading the correct Arduino driver code, you can make that talk CAN. And that particular board has a jumper. If you put the jumper on, it terminates it. If you don't put the jumper on, it does not terminate it. Now, if you've got a, like in my case, I've got a ST Micro eval board that has some kind of Cortex M4 processor on it. That processor has 2 built-in CAN peripherals. If you want to use it, you have to add an external CAN transceiver to that. So you have to go out and buy a board that's about a $3 board, and it's just got a single chip on it, and you just hook up the transmit and receive data between the 2 boards, and you hook up power and ground. And the boards I have either come with a termination resistor soldered down that you can't disable without taking a soldering iron and popping it off, or you can get ones that again has a jumper. So you put the jumper block on, it terminates it, or you pull it off and that goes away. So that's something to look at when you get the little transceiver or the transceiver boards. And there's different ones you can buy, and some of them run at 3.3 volts, some run at 5 volts. So you have to make the logic side match whatever your peripheral or whatever your processor is to get those to connect. Once you get out on the CAN bus, I don't think it cares what the voltage is, because you can run, because the 3.3 volt transceivers work just fine on a CAN bus, and also the 5 volt ones work just fine. And probably if you had I think you put up like 12 to 24 volts or something on the CAN bus without burning anything out. So, but again, you want to match your transceiver board to whatever your peripheral is on your device. Now, my only experience with CAN bus on the NVIDIA stuff, we had the TX2 board, the standard eval board, and it had 2 CAN buses built into it. Again, they were just the peripheral built into the chip, and I had to add the external CAN transceiver. So I picked the one that was the 3.3 volt compatible, and I don't have that number handy, so I can't tell you what the part number was, but it was like a $3 board I hooked up. And I think I wired up both of the CAN interfaces on the TX2. And then once you get that wired up, and the ones I had, the transceivers had the termination resistors soldered directly down to them. So I had both of my 2 CAN nodes, CAN endpoints terminated. So I just ran wires between the 2 boards to get that to work. Now, once you're doing this in Linux, Linux is smart enough to know about CAN, and I can't remember what all the different pieces are you have to download, but you have to download one, what do they call, what are the Linux drivers called? You do ls mod, what are those things called?
Can utils?
Well, I mean the actual driver. I can't do what you call the drivers under Linux, but you have to download a driver for the specific chip that you're running. So if you're running the microchip board, you want to download it's MSP 2550 driver. And in the case of Linux on a AVR board, so if you've got the NVIDIA Jetson board, it's got the built-in CAN CAN peripheral. You have to figure out what driver goes with that. Now, it could be that a lot of the stuff, when you get it, they've already got the drivers loaded into Linux for you, so you don't have to go track them down. And I was thinking on the NVIDIA stuff, they do already have the drivers loaded, so you might have to do an ls mod to load it. So you have to say ls mod CAN, ls mod, and then whatever the peripheral chip is. And I don't remember if those boards have that microchip MCP 2550 or whatever it's called. That might be the one you have, but you have to load one of the low-level drivers for the actual peripheral. You have to load one for CAN, and I think there's like a third one that you have to load. And then once you get all that loaded, then you have to load up socket CAN, which somebody just posted with an unknown 834 timestamp, it's going to say, so we can check that later. So you have to load that up to get Linux to talk to that built-in driver that's on the thing. And now Linux understands CAN at that point. So when you start this up and you initialize the port, it will show up. If you do an IF config, it'll show up like an Ethernet port. So you've got Ethernet, you've got something else, and then you've got CAN. So it'll say CAN 0, and it will show you the device out there. So basically, it's treated like an Ethernet network, but it actually runs CAN. And as I was saying before, well, if you're gonna run CAN, go into your go into the configuration for that. I think you do like IF config, and then you do a command that says add this, and you say something like TX buff, transmit buff, and then put a bigger number than what they give you. If you don't, it defaults to 10, and that'll bite you if you're trying to send data quickly from ROS, because you write a ROS node that says, okay, I want to, here's a node that's going to do any arbitrary thing you want. But when I do that, I want to fire off 6 CAN messages in a row that is going to be sent to a different device or maybe several devices. And as soon as you say, load up those buffers and say transmit, bam, it shoves 6 CAN messages into this buffer. And if you only got 10 to start with, that's going to come back to bite you real quick, because if it doesn't immediately send those, you come back around and it's going to error off and give you some strange message you won't understand. So what we would do, at least what I did, was I looked at the message under IP config for Ethernet, and it says something like transmit buffers is like 1,000 or something like that. I just arbitrarily made my CAN buffer 1,000 also. So I could just take a whole block of messages and pound them out at once. And Linux is responsible for doing all the buffering and all the magic behind the scenes. It'll take care of all that for you. But make sure you got that buffer set big enough, or it's going to give you some stupid error message that it takes you days to track down what that's actually trying to tell you. So once you get to the point where Linux understands CAN, which is what the socket CAN stuff will do for you, you have to load that. And then as Vinny points out, you download CAN utils, and that gives you things like under Linux, you can say, there's a CAN dump command. So you say CAN dump space CAN 0, and any message that comes in on CAN 0 will be printed out on the screen, so you can see all the messages going by. And there's one called CAN send, and you can say CAN send, and you might give it a parameter, and you type out the 8 bytes or 4 bytes, whatever you want to send, and then hit enter, and that will send that message out on the bus. Or something under CAN send. It's either CAN send or there's a different message, and you can say basically tell it just send random data and send it with random byte length, and the thing will just start generating messages and sending out. And that puts them out like, I think like 10 times a second, but you can put a dash something on there for speed, and you can crank those way up so you can really start flooding the bus with information without having to really type anything in else in after that. So this is all still at a Linux level. This is all initializing the interface, and then by doing the CAN send and it's either CAN dump, I think is the other command, you can watch the messages going back and forth. And you can have multiple CAN interfaces on one Linux computer. So you can go to one window and say CAN dump, CAN 0, go to the other screen, say CAN send, whatever parameters, and say start sending random data. And then you'll see on the other screen, all the messages going out, you'll see them coming back in on the other one. And if you want to, you can have multiple CAN devices on this bus. So you could have, say, 3 Linux computers. One of them is sending out random data. One of them is just dumping the data, and the third one you're actually controlling or whatever. So once you get all that set up, this is all, again, all from a Linux level at this point. And down to the fundamental CAN level itself, you can send anywhere between, I think, 0 to 8 bytes per CAN message. So if you want to send a lot of data, that gets a lot more complicated to do that. But in general, if you're talking to a motor controller, and you say, I want you to run at this RPM, or this, you want the vehicle to run so many meters per second, you just have just 1 or 2 numbers you're sending out in that message. So there's a lot of things you can do with just 8 bytes in a message. But when you get to the point where you, for some reason, you've got a device that wants to send 256 bytes, well, now you're in trouble, because you can only send 8 bytes at a time. So they've come up with other protocols you can add on top of everything else that will They have one thing, I can't think what it's called. They have a protocol that might be under ISO 11787, 117, whatever that is. There's yet another protocol they throw on top of all this that says this is a multi-packet message, and it'll say you send out a message saying I'm about to begin a multi-packet protocol, and then you have to wait 250 milliseconds, and then you start sending the packets out with a delay between each one, and then when you're all done, you say that's the end of the multi-level protocol. And that took forever to send stuff out that way. So when they came out with NEMA 2000, which is yet another one of these multiple protocols you can load on top of everything else, they came out with one that they threw out a lot of the nonsense, and they just said, we're going to send this type of message with this number of bytes, and just automatically packs all these together and sends about just as fast as it can. So again, when you start digging into this, it gets really messy trying to figure out how to do it. But if you just want to send a simple message from point A to point B, it's up to 8 bytes. That's fairly easy to do. You just load up your array with the bytes, you call the transmit, and it just magically shows up to their end, and there's your data. It's ready to go. So let's see, why did I go down this path? Blah, 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 multi-bytes. So if you get to something like, say, an ARM processor, like on the NVIDIA boards, it may or may not have all the drivers loaded. When they compile Linux, they may have loaded all the drivers in. So if you just do the ls mod, it'll tell you if you've got you need CAN, you need the CAN driver and something else. It'll tell you if those are loaded. If not, then you do the, what's it, ins mod, or there's another command that says load those drivers. And it's never clear to me if you load it once, if they stay there, if you have to do everything to start it up, every time you start it up. But anyway, you have to do that to initialize the thing. So then once you get to the point you want to run ROS, okay, so you initialize the CAN interface before you start up, then you start ROS. Now you need to have a ROS node that will talk to the Linux CAN interface that's in there. So if Linux is running socket CAN, then you have to have, I can't remember what the name for it is, but somebody's got a standardized node that you load into ROS, and ROS knows how to talk to socket CAN on one side and then do topics in and out on the other side. So you have to load that one up. So then in your code, you write a node and say, I want to send this over the CAN bus. So you say, load up my 0 to 8 bytes of data in this array, set the byte count I want to send, and then you do a ROS publish. It puts that on like I think they call it like the transmit. They have something cryptic like just simply transmit and receive are the two topic names, and you really should qualify that more so you know what that is compared. Like either you qualify that as CAN, you might want to even call it CAN 0 transmit and CAN 1 or CAN 0 receive. So go ahead and rename those in the process so you know what they are. But anyway, in your node, you just load up the array that you want, and you call the publish, and it will publish that out on, say, we'll call it the transmit topic. So then this extra ROS node that I can't think of the name of, it'll get that as a callback and say, oh, somebody wants to transmit on CAN bus. So it takes those bytes and shoves them into the proper format, and then calls the socket CAN interface, and then it passes over to Linux, and Linux just magically takes care of everything else for you after that. And the thing to keep in mind is you can have multiple CAN buses running on any particular computer if you want to. So on your NVIDIA, I think it's probably got 2 CAN peripherals built into it. And I think Walter just said he had to add CAN transceivers onto that to make it work. But what you do, you can either run just one CAN interface, or you can run both CAN interfaces if you want to. And another point on that was we had the SwiftNav GPS. And when they first came out with that, they said, oh, it's got 2 CAN buses built into it, but you have to add your own transceivers onto that. So I went to the trouble of hooking those up and following their examples. And sure enough, the 2 interfaces would talk to each other, except that when I tried to connect those to anybody else in the world, it wouldn't talk. And after several days to several weeks of digging around, I found out that they've screwed up something in their software where the baud rate that you specify is off by a factor of 4.8 times. So instead of putting in, I think we ran 250 kbits per second, and I had to put in like 1.2 megabits per second for the thing to understand it. There was some drastic number difference there. And it turns out over time that they apparently decided either nobody was going to use that CAN bus, or it didn't work right, or whatever. And they don't even mention it anymore. It's built into the hardware, but there's nothing in the documentation that tells you that it's there. But it did indeed work after I figured all the little details to that. So other things I mentioned, the Arduino, you got to put the whole extra controller board on, and that it's a $5 board. There's code you download, and that will work. Or if you get the like the STM micro boards, they've got built-in peripherals. You have to put the external transceiver on it, and you got to go track down the code and get that to work. But that seems to work well once you get it running. If you buy the Teensy boards, the Teensy has the built-in peripheral. You have to put the external transceiver on it, and you go to the Teensy examples. They say download this and CAN will work, and it does. It actually does. You just download the code, so you can get a Teensy to quite easily talk CAN. And the NVIDIA boards have it built in, and a lot of the modern AVR type processors already have that built in. So if you buy anything that's got the modern AVR processor on, you've probably got a good chance of it being able to talk CAN. There's something else that just came up I was thinking of. Oh, and then of course, people like Matt was, oh, are you using J1939? Are you using ISO 11783? Are you using NEMA 2000? Are you using OpenCAN? You can this or can that? Well, it turns out if you do it down at the hardware level, you just simply got 8 bytes. You got an array of 8 bytes. You load up anywhere between 1 to 8 of those bytes. You set a byte that says, here's the number of bytes I've got. And then you've got this whole concept of the ID on CAN, where it's either an 11-bit or a 29-bit ID field. And if you're running straight CAN, you can do anything you want with those bits. And they got this magical thing where when it starts sending the data out, it starts, the first bit that comes out, it looks to see if it's high or low. If you've got 2 devices transmitting at the same time, if they both start at exactly the same time, and we'll say if both bits are high, that's an acceptable thing. You go to the next bits, those are high, that's acceptable. You go to the next one, and one of those is low. Whichever one, it looks at it because it puts out a bit and says, I expect this to now be low, but maybe it's still high, or the other way around. And the one that does not have the highest priority will just automatically back off. So you don't have to have a master slave where you say, you go out and ask the master, can I transmit now? You just simply blast your message out. And if somebody else starts at the same time, and whoever has the bit in the wrong position first has to back off. And then they go into a delay cycle. So you wait like 2 or 3 milliseconds, you try sending your message again. So all that works.
What happens if they have the same CAN ID?
Well, it depends what you mean by CAN ID, because inside of that header, you got like a transmit ID, a receive ID, you got priorities, because if you've got 21 bits, there's a lot of crap in there. So when you say, what if it has the same ID?
There's like a PRN number or something.
Okay, well now when you're talking PRN, you're talking about all these exotic protocols they put on. I'll get to that. I'll get to that in a second. So you start off, you got either 11 bits or you got 21 bits. And I don't know, I guess 11 bits wasn't big enough for them. That's what, is that 2048? Let's see, 10 bits, 1040. That's like 2048 different things you can put into this. They say, oh, that's not enough. We need 21 bits now. So if you're doing it the original way, I think it starts off like the first 3 bits are like priority, and then there's a couple of bits that I don't know what they are, and then you've got like a big field for like transmit ID and a big field for receive ID and some other stuff. So what they did, somebody came along and says, oh, well, that's great for Bosch on talking on their cars, but oh, that doesn't work well for us. We want to use it for something else. So they said, okay, well, that's when it came. I think that's where J1939 came in and says, well, we'll break those bits up into some kind of fields, so that'll keep people from complaining for a while. And they say, oh, but we want to run it for our nautical vehicles. We want it for tractors. We want it for something else. So what they did, they just took that whole big ID. When they got the 21-bit ID, they just whacked it off and said 0 to 1,000 we're going to give to this company, and 1,000 to 2,000 we'll give to this company. And as they started doing that, all this original functionality with all this magical stuff about the backing off if you're trying to transmit and don't have the highest priority, all that got thrown away because they decided how to wedge all this other stuff in there. So if you go look at it, it turns out anything that's CAN open will be a certain ID range. Anybody that's whatever, I can't even think of what all of them are. And once you start looking into it, there's way too many standards out there. and they all act a little bit differently, and they're not directly interchangeable. You can put them all in the same bus, and as long as you stay within your address range, you can probably get two, two of, say, the NEMA 2000 things to talk to each other, at the same time have two of some of the other standard to talk to each other, but they can't necessarily talk to each other because they don't fit within the right address range. So when you start looking at it, that stuff starts getting fairly ugly. So you just have to say, I just bought this thing and it talks, say, can open. Well, can open is going to have a certain address range, and they're going to treat all those bits differently depending on what format you have. So you got to go look all this stuff up.
So in ROS space, right? Do I have to do anything different to be talking J1939? Or is it just a matter of populating the frame message appropriately?
At the lowest level, it's just a matter of populating the frame ID correctly for whatever you want to do. And think of a UART. If you've got a UART hooked up that's just sending data from point A to point B, and I say, I want to send the letter A, I just slam it out and it goes. Well, then someone that comes along and says, well, I want it better than that. I want to have multiple devices with addressing. So somebody makes up new protocols to put on top of all this stuff. So it really comes down to that at the lowest level, you could load up the fields and do anything you want with it. And then as soon as you lock onto somebody's protocol, which you may be forced to do that, because if you buy, say, an off-the-shelf IMU or an off-the-shelf GPS or whatever it happens to be, they're going to say, oh, well, we're using this format. And then you have to adhere to whatever it is they're trying to tell you to use. And the other option on that, the other point with that is, then you run into companies, we bought an IMU and they said, oh yeah, we made it talk CAN. So what standard are you using? Oh, we just made it up. We just put in whatever we want. So then now you got yet another problem that may or may not work with anything else that they want to plug into this vehicle. Say in the case of like a John Deere tractor, they're going to have all their stuff set up with certain address ranges. And as long as you don't conflict with those address ranges, you can go on, you can transmit and receive messages between any other two devices, as long as you don't conflict with what they have. But then, like the problem with John Deere is they say, well, we've got all this marvelous stuff set up, but we're not going to tell you what it is. It's all proprietary. You can't touch it. You can't do anything with it. And if you look at it hard enough, you can figure out what they're doing. In some cases, you can make it actually work unless they've got it fully encrypted or something. But at the lowest level, it's just up to you. You just load it up and say, I want to take these 8 bytes, send them to this device over here. It's going to receive them, and everybody's happy. And then if you say, buy a device, say an IMU that's putting out, they're going to say, here's what the device ID is. And then there's lots of other things. Depending on the range of the device ID, that's going to define it as somebody's standard. And then you might have to go adhere to different bits out in the header to do different things. So it turns out every time I try to add something, you have to go look it up and dig through all the documentation to find out, what is it actually expecting and how do they want it to work. So that's when everybody tells me CAN is great, it'll solve all your problems. I think, well, I've dealt with it enough to know that you're opening up a can of worms if you want to use it, but feel free, go right ahead and use it. If you're doing it for yourself, it's just, hook two devices together and you can put anything, you can send anything you want back and forth. It's just, if you have to start working along with somebody else, then you have to say, okay, we got their device. Here's their requirements. We can't stomp on that. Or if we want to read their device, you have to know what the fields are they're trying to tell you. So you have to figure out how to decode or encode the data to deal with that device.
And then my second question is, when you Google socket CAN ROS, there comes socket CAN interface, which I think Matt posted, but there's something called socket CAN bridge. And I'm very confused what the difference is and which one is the right one to use.
I think socket CAN bridge might be the ROS node that you need to make this work. So socket CAN itself is just Linux. That's all behind the scenes Linux. You have to have that running to make it all work. And then I think socket CAN bridge is the ROS node. You start that up, and that knows how to connect to the socket CAN layer and how to talk to ROS topics on the other side.
No,
so they're just like 5 or 6 things you have to all stick together to make this stuff work.
Yeah. No, there's a ROS package called socket CAN _interface.
Right. offhand. It's been long enough. I can't tell you what all these different things are. So,
Okay, that's fine. I'll, you know.
but if you find somebody's tutorial that says how do you make Ross talk CAN, they'll say you hook up this and this and this and this, and you can do it that way, or there might be other ways to do it, and you know you find different descriptions and different nodes you connect together to make this stuff work. But
Okay.
there is enough information out there. Even I figured out how to do this and got it to work. So
Okay.
it is possible. It is possible to make it work.
And then my other question is that buffering thing you're talking about earlier. Like roughly, how did you do that? Like, is it simple? Is it trivial? Like, I don't even know what to Google to do
I
that.
mean, how to change the buffer size?
Yeah.
I think it's just you say ifconfig, and then there's a like a dash something for the option, and then you say transmit buff, and you say 1000. So that's just a command line thing you type in. I think you have to type in every time you start it up. You have to put that in.
Okay, but it's ifconfig.
I think that's where it's at. Yeah. And if you just search for ifconfig and buffer size, it should tell you whether it's for Linux or whether it's for Ethernet or CAN or something else. I think it'll give you the commands on how to do it. Or just go to your command line, type in ifconfig -- help, and you're just going to give you 500 options. And one of the options is change size of transmit buffer, and they'll tell you what to type in for that. I think that's how we did that. One more point is if you've got standard Linux and you buy somebody's little board, which I don't have a board laying here, but you can buy these little $20 boards that has an ARM processor. It's got USB on one side and CAN on the other side. Those all run, so I think it's something called SD CAN. I don't know what SD stands for, but maybe it's SL CAN. But basically, one of these little drivers you have to load with the ls mod or ins mod command. You have to say load. We'll say it's called SLCAN or SLCAN-D. I can't remember which it's called, but you have to say load that driver. And then when you actually initialize the part, you go to the command line and say something like SLCAN-D dash whatever, and then you put all the parameters there. So you say here's sometimes you have to tell it the baud rate between the baud rate over the USB. Sometimes you have to specify that. If it's an ACM device, you don't have to do that. But if it's a USB, like USB 0 device, you do have to specify a baud rate. Then you have to specify the baud rate you want the CAN to run at, which is going to be, you know, like 1 megabit per second or 250 megabits per second, whatever that is. You have to specify that. And there's like two or three other things you have to specify. So based on the actual physical interface you're running, you have to give it a command line to initialize that. And I'm thinking that NVIDIA has that stuff all built in, but you still might, if you go out and if Walter's got running, he can tell us what the commands were to do that. But you probably, when you first start it up, you probably have to say, it might be running the SLCAN-D, and then you got the parameters to tell you what the interface looks like and how it works. And then otherwise, you know, whatever you plug in, whatever physical interface you plug in, you have to get the right command and the right parameters to make that work. And one of the simplest things to do is get whatever, it's nice on a machine that's got the two interfaces built in, like I'm sure all the NVIDIA parts do. I think even the NVIDIA Nano, the Jetson Nano has the two interfaces. So you put the two external transceivers, you wire the two back to back, and then you can go right into Linux. You can say, load up the transmitter side and then load up the receiver side, and then load that CAN test stuff. And you say, CAN send on say CAN 0, and you say random data, and then go to another window and say CAN dump CAN 1. So anything that comes in will be displayed. And that's the first thing you run, just to prove that Linux itself can send CAN messages back and forth. And none of that has anything to do with ROS. That's just a matter of how do you get yet another random interface on Linux to work. And if you get that to run, and as Walter was saying that he couldn't get it to do anything, but he put the resistor on and started working. There's something on the CAN bus. I think if it doesn't see the right condition on the bus, it won't try to transmit anything. So you can send a few messages out. It'll send out like 2 or 3 messages. It'll come back and say, oh, timeout error, no transmit buffer space available, or something like that. But if you go out and you stick a terminator resistor on, and bam, you see the received messages, all the messages were queued up, and they'll all pop up now because something about it is looking for the right condition on the bus, and it can't see it. It'll just sit there and wait. First of all, Linux will time out So it'll send all the way back to ROS and say, oh, can't do it, no buffer space. But once you put that termination resistor on, that makes the bus happy. And all of a sudden the actual CAN hardware will now push out whatever data it had buffered up there, and you'll see it show up on the screen. So it's just little things like that you find out too, that after a while, I know some of the times I'd hook up these interfaces and they would work whether I had hooked up to anything or not. And other times they wouldn't talk at all until I'd plug in the termination, and then it would come back and fix itself. So they're just more, it's adding more mystery to the whole thing. Once you finally get it figured out, you get the thing wired together, it's all working, then theoretically every time you fire it up and go to run it, it should work, until a random error pops up that you go to Google and say, what does this mean? And they'll give you some cryptic response and take you through all these old drivers. You got to figure all this stuff out. But once it's running, it seems to work fairly well, I guess. And that's all I want to complain about at the moment, I guess. There's other things that will come up in the fact that when you go out and buy a device, they'll say this runs at 500 kbits per second, and they don't give you any way to change it. So that means you either have to have the interface on your computer or on your main computer. That one has to either be set to the same baud rate, or if you're lucky, you've got more than one interface. So if you want to run one set of devices at 250 kbits per second and run the special one at 500 kbits per second, then you can actually run the two separate interfaces to do that. And we ran into that because we bought a Delphi radar, which is like a $5,000 peripheral box we bought. And it says, oh no, we only run at 500 kbits per second. So we had a dual channel CAN interface plugged into into a desktop computer. So we set one channel to run at 500 kbits per second just to talk to that. And then the other bus would talk at the 250 kbits per second that everything else ran at. So little things like that will come up too, that you've got to, because you got to match the baud rates to get them to work. And then if you're really crazy, there's something I think it's called CAN FD, which is maybe it's not called FD. Something about it can run at multiple baud rates, so you can mix different baud rates on the same bus, and that's something we never got into that because all the stuff we're using had a standard. You grab an off-the-shelf product that our company made. They said it will run at this baud rate, and that's all you had to worry about. But they got this more modern stuff where I think it can actually run different baud rates on the same bus, and normally that'll crash everything if you try to do that on if you're not doing all the extra special funny little things that you have to do.
Jeff, is buffer size related to the baud rates? Is that mainly for the traffic control, right?
Well, the baud
like
rates,
changing the buffer size is what we can use it for.
Well, if you got two devices that you want to connect together on a bus, they both have to run at the same baud rate if you want it to work. So right. if you buy somebody's device and it says this is the baud rate it runs at and you can't change it, then you have to make sure your end is set at that. Now, most devices you buy will say, here, type in this command, you can change the baud rate on the device. But it's like on a UART interface, both ends have to be running the same baud rate to make the thing work. And on CAN bus, if they don't match, everything just crashes and you don't know why. So that could be another problem that you run into. And then there's more things that you get involved with that mainly I didn't deal with. There's something about called, I think it's called bus on and bus off, where you can say, here's my peripheral node. I want it to go on the bus, and then it starts actively talking, or you can say go off the bus and it won't affect anybody else. There's more things like that that'll pop up that again, most of the stuff we had would just automatically, you'd power it up and it would go on bus, you plug it in and it would work. But there's more elaborate things you can run into as you go through all this stuff. So start with the simplest thing you can. Get two devices to talk to each other, and then if you can find somebody else's device you want to talk to, try to look at their specs and see what it take to talk to that, and see if you can get that to talk to your Linux computer and or to ROS directly, and then go on from there. If you're making your own devices, if you've got your main computer and you're going to connect it to, say, you've got your own IMU with a microcontroller and you want it to talk CAN, try to write the code to get that to talk on the CAN bus, hook it up to your big computer, and see if you can get that to send data back and forth. And then once you do, then you can start adding more and more devices onto it. See see what comes up and see what works and what doesn't. I guess other than that, I don't have a lot more words of wisdom at this point, other than you're going to have to try it and see what works and see what doesn't work, and then decide if it's worth doing or not. One other thing I could point out is that, you know, as Matt keeps pointing out, well, it's very noise immune. You don't have to worry about it. Well, it's got noise immunity because the CAN bus is a differential pair, which means when you want to send a signal, the high side and low side are opposite of each other. So as they flip, see, normally it sets where we'll say the high side is always high and the low side is always low. And when you flip the bit, then they flip positions, so that the two like this, they're like this or like this all the time. And then by running that over a twisted pair, which somehow increases your noise immunity at the receiver end, it's looking at that. And as you got noise that's bouncing up and down like this, you got two wires like this, and you got the signal bouncing up and down like this. Well, if this has the signal, that has the signal, it just subtracts those two off. So the resulting thing is it still sees just this bit and this bit. They're either in this condition or then the opposite condition like that. So that's what you see at the end. And there's various things that use differential twisted pair. USB actually is set up with differential twisted pair. So USB is probably fairly noise immune. And then if you, in the serial world, if you run an asynchronous serial, you can run RS-485 or RS-422, which is basically you just take the data line and they add that differential transmitter and differential receiver to the two ends of the cable. And so that can also be quite noise immune also. So in reality, yes, CAN probably is quite noise immune. And one difference between that and RS-485, I always thought that RS-485 had to have a ground reference between your transmit box and your receive box, because theoretically you don't have to have these on the same machine. You can put, I think the RS-485 says you can run either 1 megabit per second or something like 1,000 meters, or some combination of the two. So you can run shorter distance at higher rates, or you can run a longer, you know, you can either lower the rate and transmit shorter distances or go the other way around. And the CAN bus, I don't remember what the numbers are, but they give some values on that say, you know, how many meters long can the cable be. And once you get into a big system with a lot of cable, then they start getting cranky about the fact that you have to have, say at this end, you've got your computer here, it's got a CAN bus, then you're supposed to have a node here, a node here, a node here, and a node here, all strung out along this cable. And then at the final end, you got your final device with a terminator. So you terminate at this end, you terminate at this end, and you can have, you know, hundreds of devices in between. And that's the way you're supposed to wire it up. It turns out you can wire up in like a star configuration, just a small thing running on your desk. You can wire it up any way you want. Just put the CAN high in parallel with all the other CAN high lines, and the CAN low in parallel with all the other CAN low. And you have to have at least 2 terminators on the bus. So earlier somebody mentioned 120 ohms. Technically, you're supposed to have 120 ohms at this end and 120 ohms at this end. But when you put 220 ohm resistors in parallel, you get 60 ohms. So if you wanted to, you could just put a single 60 ohm resistor somewhere, and that will electrically keep everybody happy for the fact the bus will run. But by having the big long cable with a terminator at both ends, it goes back into if you're an electrical engineer, you know about transmission lines and reflections and all kinds of stuff like that. Somehow it's supposed to solve all that. So if you have your twisted pair terminated at both ends, that's supposed to be a nice, quiet transmission medium. But as I say, if you just do it on your desk, you just got 6 inches of wire on everything. You just wire them all together and it will work. So as soon as you put it onto your lawn tractor or your full-size John Deere tractor, or you got your John Deere tractor with an implement on behind with another 10 meters of cable going back to that, then you may have to start adhering to all this concept of the everything's got to be on a single, but I can't think what the term for that is. It's just a single wire that goes from the first device all the way out to the last device, and then you've got these devices in between that are connected to it. So it can get more messy depending on what you're trying to do. But just to get it to run, you hook 2 devices together on your desk, and it should work. I guess I don't have any actual horror stories. I'm sure there's a lot if I think about it long enough that, there's times when I would waste 2 or 3 days trying to get something to talk, and it was either something simple or it was a parameter or something about the wiring. Oh, the other point I was going to make, I was saying on RS-485, I think you're supposed to have a ground reference between the first box and the last box. And on CAN, it doesn't seem to care. They will say you can have the 2 data lines. You can have CAN high and CAN low. And then usually they'll have a shield on the cable and they'll tie the shield at least one end. But apparently you don't have to have a ground reference between the 2 boxes, which means you might have 20 volts of difference between the 2 devices for whatever reason. But based on that differential driver, it doesn't care. It's just looking for the difference between the 2 wires you got out there. So it's as if you're running 3.3 volt transceivers, you're going to have a difference of 3.3 volts. And then when they pull together, let's see, how does that go? Because the way CAN works, if you look at it on a scope, you've got the 2 signals like this. And then when the signal goes active, I think it pulls them together like this. So they're close to like 0 volts down here. There might be 3.3. Or if you got a 5 volt one in the line, it might go all the way up to 5 volts. But it doesn't seem to care about that. It's looking for the difference between the 2 outside ones and then close to 0 in the other condition. And whether you have, say, you got this one here and this one over here, where this one's way down here. This drives me crazy because the screen's backwards. This one might be at, say, minus 5 volts, so it might be at plus 10 volts. It doesn't care because it sees them both switch at the same time, and that keeps everybody happy. So that's just one more thing you'll run into. And when you first see it, well, it doesn't have ground hooked up between. Well, apparently it doesn't need that. So that's just more esoteric things as you go down the line. You'll run into this kind of stuff. So let me go back to Walter and say, okay, you've got CAN running on an NVIDIA. What do you plan to do with that? Are you trying to talk to somebody's off-the-shelf peripheral? Are you going to have 2 NVIDIAs talking to each other? Or you just wanted to prove that you can make it work?
Well, he dropped.
Oh, well, okay, we won't ask him then. So back to Matt's concept where he says, well, let's make the lawn tractor all CAN bus activated. Number one, to get rid of the noise. I think it was the main topic on that. So on the lawn tractor, for anybody that's not following those projects, essentially make your lawn tractor go forward and backward. Everybody has picked one that's got a hydrostatic transmission, which means it has a single lever on the transmission. If you move the lever forward, the thing goes forward. If you move it backwards, it goes backwards. You move it back to the center, it comes to a stop and locks up the transmission. And right now, everybody has either a linear actuator, electrical linear actuator, or a giant RC servo to move that arm back and forth. And then that's just tied directly back to the microcontroller to activate that actuator. So what you could do is you could take that device, and whether you're using a linear actuator or a giant RC servo, basically you could build a module out of that and say, take that actuator and get a little microcontroller to control it, and put a CAN bus on that. So we could then put a CAN bus and just vehicle power onto this thing. So we can send out a message that says, I want you to move it forward 10%. So you would send a message across the CAN bus, and it would say, okay, to figure out what 10% is, you'd have some kind of scaling values inside of this thing, and it would know. So on the thing, you got this giant RC servo and moves it forward 10% of the full travel, where full travel might be out here. So it just tells it what position to go to, and just automatically would do that for you. So now you can create a module, and you say, in this case, you'd say set a position, and it's up to the module to do that. So you can either have local closed loop feedback, or on an RC servo, they're usually set up, you just give it a certain pulse width, and it goes from here to there. It just knows how to do that. But you could have a thing inside of the thing here that reads the position out and corrects for it on the fly. But in that case, in order to control the vehicle speed, you're just saying, send a position out to this smart module. So you write a CAN message that says CAN ID 3, and that could be, you got 21 bits out there, so you can have any number you want. But we'll say, send a message to CAN ID 3, and the first byte is going to say, here's the position I want you to set it to, or if it's a 16-bit number, use the first 2 bits, or first 2 bytes in the thing. So you send a 32-bit number, and that translates into position, and then it will just automatically do that. Now, if the thing happens to have built-in feedback, which on the giant RC servos, you can solder a wire on the potentiometer and read that with an A to D converter to say, I told it to set it to 10%, but it says it's at 12%. It can automatically correct for that. And then if you wanted to, you could send that as a CAN message back to your main controller saying, you requested 10%. I'm currently at 12% or whatever. You can define your own protocol in between there, which may or may not be J1939. So anyway, you could create a module just to do that, and that same thing would work. Basically, the same thing would work for steering. So on the lawn tractors right now, everybody's put a power steering unit from a car onto their steering of their lawn tractor. So basically, it gives them a big DC brush type motor that could turn the steering column back and forth, and then you have to put a big power driver on that so you can convert the low-level microcontroller signals into, say, 10 amps or whatever it takes to turn that motor. So again, you can put a microcontroller on that, and that would probably have some kind of feedback built into it anyway. So again, you put it on your CAN bus and say, okay, say CAN ID number 4, which is going to be our steering. You say, go to this steering angle, and then the microcontroller would then turn the motor one way or the other until it lines up with its whatever position you tell it. And then also, if you're reading, to make the steering work, you generally have a feedback signal, say a potentiometer or magnetic sensor or whatever you want. And so the microcontroller knows what position it's in. So you can send that back over the CAN bus. So over the CAN bus, you can say, what is the current steering? And it'll send back whatever angle it is. So now we could have a second device that's also on the CAN bus that will control the steering. And the first CAN bus we define is on the CAN bus, or it's on the transmission, define the speed. So then each thing you add onto it. So you say, okay, well, let's add something else. Let's put some sonar on the front of this so we don't run over anybody. So you could take another microcontroller and hook 1 to, say, 10 or 16 sonar modules to that. So the microcontroller is smart enough to scan across the individual sonars and get the positions. And you could either say, send back all the positions over the CAN bus, or you can say, if anything is less than 2 meters, then send me back a message saying we've got a problem so we can shut down. So each thing you add on could just be a new CAN module, and you just stick those on the bus. Each one has to have a unique ID number. And what some people do is, gee, we got 21 bits. That's a big number. We'll just say all of our transmission control will be, say, ID 3. The steering will be ID 4. The sonar will be ID 5. Maybe we got flashing lights to be ID 6. So you can predefine what you want all these things to be. So now it's just a matter of sending out either directly from your ROS computer. You could have a ROS node that says, set the forward speed to this, and it would put it out directly over the CAN bus, and you wouldn't need any intermediate microcontroller. But I still prefer to have, on my vehicle, I prefer to have this low-level microcontroller that talks over an interface, say USB, to my ROS node. So the ROS node says, set forward speed to 1 meter per second. It sends that down over the USB to my low-level board. The low-level board would then talk out CAN saying, send a message to my transmission controller to set whatever appropriate angle it takes to make it drive forward at 1 meters per second. Now, in my case, I've got a big electric motor instead of a gasoline engine and hydrostatic transmission. I have an electric motor, but it could be done the same way. I could make that a CAN bus device. And really, if you think about it, the actuator for the transmission and the actuator for steering can work exactly the same way. It's just the actuator on the steering is a much larger motor in order to move that. So you can even go with classifications and say, I want this actuator to control speed. I want this to control a position or whatever. And you could theoretically have one device to do everything, and you send out a parameter saying, I want you to represent speed. I want this to represent a steering angle, and just use the same. So you could even have the same code on all these different devices. Now the larger motors need larger power drivers, so there's more things involved there. But you could indeed make all your devices a CAN bus device and put them all on the same bus and theoretically get everything to work just fine. But you just have to start somewhere, and I see Walter's jumping in and trying it, so we'll see where he gets with that.
Plug and play. Sounds easy.
And just for the heck of it, let me put in another timestamp so I can check this later. 19. Okay, so I check that later if we go back and check the recording. So any more questions about CAN bus? Anybody
One-
want to tell me how great
one
it is
qu-
without actually trying it?
Yeah, that's very nice introduction and the presentation, Jeff. So, I have a question. So, how commonly CAN bus was used in the robots, like the Husky sort of robots? Are they using CAN bus?
They
I
Like
may,
in the
think so.
commercial robots?
they may or may not. CAN bus is just a communication interface. So whether you're talking two devices, whether you're using USB or using a asynchronous serial or using a CAN bus or using Ethernet, it's just a way to get data from point A to point B. So it's just up to you to decide, what interface do you want to use to do that. So if somebody wanted to say, like on the Husky, yeah, it may have CAN bus on there. I don't know. I'd have to go look at it.